types of derivatives. If you sub in the x value into the derivative and you get 0, that means it was either a maximum, a minimum, or a point of inflection. The way to know whether it's a maximum or a minimum or a point of inflection is to then sub the x value into the second derivative. If you sub the x value into the second derivative and you get 0, you knew it was a point of inflection. Like, let's give it that. Like one of these ones or one of these ones. If you sub in x into the second derivative and you get a positive answer, you know it's a minimum. So positive for smiling. If you sub in x into the second derivative and you get a negative number, then it's a maximum, negative frowning. So this is what we call like first derivative, second derivative tests for what kind of point it is.
So it's the second. That's the main thing.
Yeah, the second gives you more detail, doesn't it? So first derivatives are going to tell you whether it's, if it's 0, that it's this. That's all it tells you. If so long as you get an answer of 0, it tells you it's either this, this, or this. But the second derivative gives you a much more detailed understanding.
Wait, no, I'm confused. I think I'm confused.
I'd probably use the first derivative test just to decide, is it a maximum, minimum, or point of inflection? Maybe it's not even any. Maybe it's just something, some other point on the graph. Like maybe it's down here, or maybe it's here.
So then, if the first derivative will tell you, why do you use the second?
To decide whether it specifically, because at the moment, if you just use the first derivative, it could be this, this, or this.
So the first derivative would indicate that it's 1 to 3, and then the second will indicate which one it is.
Yeah. So a classic question could be, show that at x equals 3, it's a minimum.
So you would know that it would have to be positive.
Yeah, so you would find the second, so I would probably use the first derivative test to just prove that it equals 0 to begin with, at x equals 3. And then, even more detail, I'd use the second derivative after that and plug in x is 3 to prove that it's whatever it was meant to be. Negative if it was a minimum, maximum, positive if it was a minimum. So they're like first and second derivative tests. If the derivative is positive, if the derivative is positive, so the first derivative, if the derivative is positive, this tells us, of course, that the gradient is positive. Because remember, like if you sub in x into the derivative, it tells you the value of the gradient at that point only. So the function is increasing. So if something's got a positive gradient, it's going upwards, isn't it? So that's another thing. If you sub in the x value into the derivative and you get a positive answer, like the first derivative, and you get a positive, it just tells us that the graph's going up at that point. Going upwards.
Confusing because it's in a negative.
Yeah, it's confusing. If the first derivative is negative, it's not a stationary point, by the way. So if the first derivative is positive or negative, it's automatically not one of these red things, because if it's one of these red things, the derivative is exactly 0. So if it turns out the derivative is positive, it just means that the graph was going upwards because it's got a positive gradient. If it turns out the first derivative is negative when you sub in x, it just means it's decreasing, it's going downwards. This is just a summary of all sorts of things that the derivatives can tell you about a graph. Let's do a few examples now. The domain. So example, write down the intervals on which the following functions are increasing or decreasing. This is nice. So here we've got the graph. Yeah, by intervals we mean domain, like using domain and range kind of notation. So where is it increasing and where is it decreasing? So this is something, maybe we'll fill it in again. Is that the whole thing? Yeah, that is the whole thing. There you go, so you can see the whole thing. So increasing, notice that it's increasing in this yellow zone only. So for the first one, it's increasing. I'll put a yellow thing because pointing out that it's increasing for the yellow bits here. So notice when we talk about domain, we're talking about the x values. So don't bother pointing out the y values. If they just want to know the intervals over which it's increasing, just talk about its x values. So it's increasing between x is 1 and all the way up to x is 5. Don't by accident use the y values. If it asks what are the intervals, it just means the domain. They want to know. More like domain notation. So it's increasing on this bit. Underneath, I wrote where it's decreasing. It's decreasing from negative infinity, because here's an arrow, so negative infinity. It's decreasing, it's going downwards all the way to x is 1. So that's one interval. And it's decreasing from x is 5 all the way down to positive infinity as well. So there's two intervals over which it's decreasing. one over which it's increasing. So good practice of our domain and range notation from last year. Notice how come I didn't put equals to on here? Why don't I put equals to on there in terms of what do those points mean? Is it increasing at x equals 1? Is it decreasing at x equals 1?
Yeah. Point of a return.
Yeah, exactly. It's a turning point. Yep. So it's neither. It's neither increasing or decreasing at x equals 1 because it's going through the turn. It's a minimum there. So that's why we don't put the equals to sign on there because it does not include that point 1. That's where it's turning instead. The gradient's not negative here anymore or positive. It's just 0 because the gradient is 0. So it's not negative or positive. See, for this little one, is this one a point of inflection? This one here?
Yeah.
Yeah.
Wonder what POI?
Yeah, that's why you might have been wondering what POI was about. That was me being lazy and not writing point of inflection. POI. So you might want to write point of inflection because in a year's time you might not remember what on earth that meant.
In a year, I would not be here.
Oh, that's true, yeah. 6 months? No way! Oh,
Okay.
don't you be gone.
Really? Wait, what month are we in?
May.
May.
No, we can't know.
I guess May. May you'll be gone right, in exam. In May you'll be in exams.
In February.
No, I exams it.
No, we don't have June.
In end of April.
You have mocks. You have mocks in Feb, don't you?
That's mocks in fail.
What is that?
And your exams normally start in May.
It's 7 months.
Am I recording?
Hey, we're born in June, though. They started in November, December.
Okay, I'm good. Alrighty, yeah. So notice this is a point of inflection specifically, as opposed to this one would be a maximum, this one would be a minimum. But this one's a point of inflection because see the gradient to the left is positive, and then and to the right it's positive. Whereas for a minimum it's positive, a maximum, sorry, positive and then negative. For a minimum it's negative then positive. Here it's negative, it's positive to the left and positive to the right. So it's a point of inflection instead.
What is 0 prime or just a 0?
Oh no, that's just a 0. Did I put that on there somehow?
Wait, what?
What did I do? I'll get rid of that because it looks confusing. There you go. Yeah, so it's increasing for both of these. There's no on this one. There's no points where it's decreasing. It's not decreasing at all for this one. Increasing over from here to here. Increasing for the green bit as well. So if you want, I can color code it. So this first bit was for the red bit. This bottom bit was for the green bit. Whereas at the POI, what's the gradient equal to? 0. Good. At the point of inflection, yep. So the gradient's 0 here, which is why it doesn't fit into here, because it's not increasing anymore. It's not positive. It's 0.
Miss Maloney,
Yeah.
why isn't
This one?
why is the next one?
Hmm.
See how it's 6 because that x is greater than 6 but less than infinity?
Yeah, I could have something
Why
wrong
isn't
here.
it negative infinity?
Where? Here? Oh, that's this bit.
Yeah, why isn't it?
This way is negative infinity,
Oh,
and this
right,
way is
I'm
positive
looking at
infinity.
it as Marine instructing me.
Ah, yeah, exactly. That's a good point. Yeah. So when we're asking for over what interval, these are all referring to x's only. We're not talking about y's, but these little y's might confuse you. So be careful of the y's. We're talking only about the x's. So the increasing ones, the first one is here from negative infinity up to 0. But then it went down suddenly, down here. It's decreasing. So that's that one there. 0 to 2. It can be very confusing, so really look very carefully and try not to get mixed up. And then, what's this one? Increasing again from 2 to 6. Oh, hello! I'll show you. Sorry. Okay, I'll show you like what it means by the thing. Like when I was typing to you, we just noticed that. So I've just typed in hi there. And that's what's happened. And I didn't want to mess it up and make it worse. So it might be something else. And the pens. Depends. Like when this morning I noticed someone had kicked it out of the back there, but it seems plugged in again, and I don't know why. Hang on, I'm just going to pause the video because that probably seems a bit insane. There you go. Okay, so what? Okay, so we're doing this last one. So this last one, from x is 6 to positive infinity, it's decreasing. So that goes in the decreasing section here. These ones, remember these kind of weird functions? What do we call these dots from last year?
Asymptotes.
Asymptotes, good. Well done. We've got vertical asymptotes going on here. So that's what I've written in there. I've written in the equations of the vertical asymptotes just for fun. Would you agree from here to here it's decreasing? From here to here? It's decreasing. So what have we done? Oh, I did it here to begin with, sorry. So the top one I did this one first. So it's decreasing from...
I'm listening to this for learning.
Have I done this right? Oh no, I'm doing it wrong. Oh, it's increasing, sorry. It's increasing, sorry. This is the increasing one. It's increasing here. This is that arm there. And notice we use the asymptotes as the boundaries. That's how we knew it's from 2 to 4, because it's from the minimum through to the asymptote. And then it's also increasing here from 4 to positive infinity.
It's 153 already?
Yeah.
What? And then why do we even do this?
And negative, fixing the board. Negative infinity to x is 0, so negative infinity to 0 for that one. And probably purple for this one. And notice it's also decreasing from x is 0 through to 2. Do you have any questions about any of those?
No, I remember this from last year.
Okay, it's good. So that was a nice little review. Now we're on to this page we haven't done at all. So this is something new, just so you know.
Yo, man, that's good.
Alright, so for the following functions, find the first derivative. And I'll let you know for the green one and the red one, it's awesome. For the blue one, it takes up loads of space. Great. So the loads one, and what rule do you think we're going to use for the blue one? Product rule, chain rule, quotient rule?
Quotient, product,
That thing? Yeah, would you agree this function it's expressed as a quotient of one function over another?
X prime. Y, I do Y prime. Take.
G prime x, yeah, G dash prime. Yep, good. Yeah, that's a very good point. Use the letters that have been used here. So G dash of x, this is just a nice regular one.
Oh no, this isn't that down at the desk. No, it's not there. I thought it might have been, but it isn't.
No, there's not been a remote in this one the whole year I've been in here.
And so it's not in any of the drawers over there.
I've not seen one at all.
Okay,
I've needed it sometimes, but
The other room that might have it would be room 3. Room 2 downstairs.
okay, let's try to go to here.
It might take a while
I
to...
think that after
because it's-
Oh, they could be white. Okay,
Okay.
alright, thank you.
And then
Okay, so find the first derivative. Who wants to say? Kavina. First derivative?
No, negative 6x squared.
Yeah, no, but I said yes, but anyway.
That looks weird, but I wrote it.
Yeah, can't speak Jamaican like me. My other siblings are from Jamaica.
Nice, I love your work.
What?
Being positive.
To Calvin.
Yes.
To me.
Yes.
Go and do it.
Just so you know, this blue one's going to take up loads of space.
Why?
So I just know from me having done it. So maybe I'm just going to put the red one down here, but it's okay. I'm going to put the red answer down here, just because this blue one's going to need a lot of space. I know from having done it. Sarah, what would be the answer to that red one?
We'll find out the square root of
X squared
Yeah.
plus 24
not.
36.
Guys, are you listening to Sarah?
How come you read all that fully not together all
I
know, but you can write it in one line.
color-coded it so you just know.
How am I going to color code it? I'm writing with pencil.
Thank you.
You can put an arrow. You can put an arrow if you want. Initially, I wrote it across like that. So if you write nice and small, you'll have space. So that's what
Yeah, I'm gonna do that.
Do you have any?
No,
No, I love it.
I don't. Cutting out. Oh, you've done it. Okay, do you want me to put this down? Okay, I'll just pause this again. There you go. Record.
Hey, yo.
I think it's recording. How do I know? Okay, it's recording. It's recording, yep. It's a different way of seeing it now. Instead of the little thing at the top, it's this thing. Oh, it's spinning. Yep, it's recording. Okay. All right, I think it is. Yep, it's recording, I reckon. Okay, so I need to scroll across. Da-da-da-da. Great. What would you use to
The product or the quotient?
the quotient rule? Yeah, exactly. Because it's the quotient means divide. So it's expressed as a fraction with a function on the top and a function on the bottom. So it's the quotient rule. Now, what on earth was this quotient rule?
U dash B dash
Yeah.
B.
Oh, yeah, sorry, yeah. What was it again? We'll write it up here.
U dash B over B dash U. You have to do no something
Something like that, though, yeah. So
U dash B plus B dash U plus B squared.
really close. Yeah, starts with U dash B. So try to remember U dash B is how it starts.
Plus something, isn't it?
That's a product rule.
Minus
Minus, good, yeah.
B dash U
B dash U
over
over.
2.
No, you were right before.
B
What is
2
that?
B squared.
B squared, yeah. That's it, good. That's the quotient rule. So remember from last year, U dash B over B dash U. I mean minus B dash U over B squared. Can you remember what would be U?
The top.
The top, yeah. And the B would be the bottom. Good, yep. So you make your own way of like explaining that to yourself. I'm struggling to write a bit with the board. So what we have to do, remember I have my little systems of doing things. I like to write out what U is. So I like to write out what U is and equals
How many would
and what U dash is underneath it. It's my little favourite way. So U is x squared minus 9.
I think that is 2x.
Good, 2x, yeah. U dash must be 2x. Exactly, you just find the derivative of U. U dash means the derivative of U. And then next to it, my favourite thing to do is to write out what B is. B is x squared minus 16. And then underneath that, I write out what B dash is.
2x.
2x, yep, it's 2x again.
Not so smart.
2x.
And then we sub all that stuff into this big formula, which is going to take a bit of space. Formula.
You know that song, guys?
By the way, if you want to, you can write dy dx equals what that is, that's the quotient rule. If you like, you can put this thing in like a little circle if it's something special.
Oh, they're both 2x.
Yep. Yeah, that's an interesting little coincidence. Quotient rule. Now we sub these things into that quotient rule. It's going to take up a bit of space. So I'm going to start to write it down here. Okay, so dy dx equals. So dy dx equals, let's start to sub in our stuff. U dash v, which is 2x. So 2x. So u dash times v. Notice it's u dash times v. So u dash v. So v is x squared minus 16. 2x. Oh dear.
That's a fire truck. Can we turn the AC off?
I know, it's a big. I know, I have
See, the
a
fire
trick.
would not have a
Your fault, man. No, this way, I have a trick.
Why don't you move?
Why don't you move, Frank? You're too hot there.
Okay.
Yeah.
Yeah.
Minus. And it's u dash v, don't forget it's minus. The product rule is the one that's got plus in it. So the product rule has plus. The quotient rule has minus. Your next screen press will be right there. Okay. All right. Minus v dash u. V dash is 2x. Bella, what's v dash? 2x, good. Calvina, what is u again? V dash u? So what do I say?
B dash U or U?
We're doing
You dash you.
You're asking you, but then you said B dash you.
Well, you know.
X squared minus 9.
You are not father.
You are not my father.
That's so much work. And that's so much work that sometimes I can by accident
You
think I'm
forgot.
done. What did I forget to do?
You
Owen,
forgot.
guys. Owen got the wrong answer, so we
Oh, so Owen, what did I forget to do?
E squared.
Never mind. Oh, that was the name.
So that's a common thing. With the quotient rule, you can forget to put in the b squared. What is v again? X squared minus 16.
Space.
Holy moly.
Squared.
X squared minus 16
We were.
squared. Don't forget squared. That's awesome. Now we've got to do all this expanding and stuff. And we've got to... Yeah, good. What was that? I'll do it over here. Okay, so Bella's now doing all this stuff. Sorry. So she's trying to talk to me. All the expanding stuff. So Bella, what did I put again to start with?
2x cubed minus 32x, and then because it's that bit.
That's right, yeah. Minus.
2x cubed minus 18.
Ooh, good guess. Just a negative 2x.
Oh,
Right.
oh, plus, yeah, plus 18.
I would have done the same thing, but it's really funny.
And with the bottom bit, quite often they suggest just leave it as x squared minus 16 in a bracket squared to begin with. Just leave it like that to begin with.
So that we can cross down, maybe?
Yeah, it's in your final answer.
We should be able to cross
They like
it
to keep
out.
it back like that, yeah. Or in the final answer, they quite often like it like x squared minus 16 in bracket squared anyway. But the top they like to be kind of simplified.
So we didn't need to expand it?
Oh yeah, don't expand the bottom for the quotient rule, because quite often the answers they want the bottom part like that, but the top part they want expanded and simplified.
Miss Maloney, you said you were going to need a calculator, but it's 10 minutes after we haven't used it.
Yeah, but that's okay. We can do the next pages, have a bit of calculator stuff, but we'll do that next lesson. Because this stuff's pretty hard anyway. Okay, so 2x, what does the top simplify to?
We'll do the x cubed gets crossed out, right?
Yeah, let's cancel that. 2x cubed minus 2x cubed.
Negative 14.
Negative 14x.
I don't know.
What was that? Why can't you just do something?
She's asking you.
Never mind.
That's done. That's done. You've just found Ruby
But
one
that
yet.
doesn't make sense.
Really? We don't have to do anything?
Yeah, with the quite often with these quotient rules, they're more than happy to just leave the bottom in the bracket squared.
I don't understand why do we
She just said
but I still don't understand. Like we could just like is it wrong if we continue to solve it?
If you expanded the bottom, it would be fine, but it's just not required. You'll find the answers in the back of the book.
Yeah.
We'll just leave it like that. I guess because in a way that's a more simple, elegant look.
How will I know what's not required in my exam and how far I don't have to go? Like, what if I don't do? I don't have to go so far. I waste time.
I reckon by then you'll have done so many quotient rule problems that you'll be just used to leaving it like that.
Okay.
Yeah, it's at the beginning that'll feel weird to you, but in all the quotient rule ones in the book you'll see that there's on the bottom. Unless it's something simple, like if it was x in bracket squared, you would just change that to x squared. But if it's something like a function like x squared minus 16 all squared, it's not wrong if you did expand it, but it's just not something that they'll require. So it's okay to leave it like that. Nice. So what's next? Oh, we've got another one down further, don't we? Oh gosh. So we just found the first derivatives of 3 different functions. Use the first derivative to state over which interval each function is increasing or decreasing. Holy moly, this is a lot of work.
we have enough time.
Do you have enough time? I'll do A with you. So a little clue is A.
She needs the first
Oh, the green one. Yeah, we'll do the green one. The green ones. So what they want? Use the first derivative to state over which function it's increasing or decreasing. So find any maximums or minimums is what that kind of is code for. So first find any maximums or minimums, and then once you've got those, they state like where the boundaries are between increasing or decreasing.
Wait, but don't you use your second derivative to find maximum and minimum?
Or minimum. Yeah, if you want to find exactly where they are, whether it's a maximum or a minimum, then yeah, you do need the second derivative. But here, all we need it is to know where's the boundary, as in like, because you know if something's increasing and then decreasing, all we need to know is what's the x where the boundary is. So just so long as you find where the derivative is 0, all we need, because the answer is like where is it increasing, where is it decreasing, kind of thing. I do see what you mean though. Oh, we're going to use the fact that there's something in the gradient, something in the value of the gradient. That's what we're going to do. You can use the second derivative. That is also possible. But imagine the question said, use the first derivative. If it didn't say, you could use the first or the second derivative. So imagine this one said, use the first derivative. Find any maximums or minimums to find out where the, and f dash x, the first derivative equals 0 for a maximum or a minimum. So for the first one, you guys found already, this is going to take up a little bit of space here. The other two will take up more space. They'll be a bit wider, so we'll just write nice and close to the edge here for this one. You already found that g dash x equals negative 6x squared, so you've already found that. And remember, if it's a maximum or a minimum, what is the derivative equal to?
0.
0. Good, yep. So let's go to saying subbing in 0.
Oh
Okay.
no.
There you go. Okay, so 0. So we can say 0
Oh yeah.
equals negative 6x squared. So now we just need to solve for x. If we solve for x, you can divide both sides by negative 6. Divide both. So Katie, what's 0 divided by negative 6?
Wait, don't we have to
Yes.
get this exploded first?
No.
Where?
No, divide by the coefficient first. You're thinking order of operations. It's probably been so long since we've done anything like that.
X equals 0?
Yeah,
Wait, why
x
would
is
it make
0.
it equal to 0?
We are just trying to find out where would the maximum or the minimum be, because remember, so we've found that there's a maximum or a minimum or a point of inflection. So maximums or minimums or point of inflection, ETC, if you've got space right or POI. State over which intervals it is increasing or decreasing. So, by the way, what was the original function?
Negative 2x cubed.
Good, negative 2x cubed. So, this is what, so we've found at x equals 0, there's a thing. The gradient is always negative. If you graph the derivative, because you guys know quadratic functions pretty well, you could probably imagine what the graph of the derivative would look like. Because you guys know quadratic
Negative 6x squared.
Yes, the graph of the derivative, yeah, negative 6x squared. Is it going to be a smiley or a frowny?
Yeah, Miley.
It's a frowny. Yeah, why is it a frowny?
Because it's
Negative 6x squared. Good. What will be its what would be the coordinate of its vertex?
0, negative 6.
Close?
Negative 6, 0.
Close? Really close?
Negative 6, 6, 0.
It's even simpler?
0, negative 6. What is it?
Negative 6, 2.
X squared, and then x minus 4 squared plus 2. That would have the coordinate. Its vertex would be at 4, 2.
Yes.
So this would be
6, 6, 6, 6, 0.
0 and
0. Oh, I was right.
0, 0, yeah. So
Zero
its
what?
vertex would be at 0, 0.
Oh,
Where you got that
break that
from?
down?
Wait, what?
No, that was just an example.
Where did you get this?
Does anyone else let out?
I have liquid whiteout.
Does anyone have empanadas? Oh, we're not
I
in.
have some enchiladas.
Okay, see how the graph of the derivative is a frowny with coordinate 0, 0, because you know that at x equals 0, there's a minimum or a maximum. So you already knew the x coordinate was at 0. And remember, like the y coordinate, the 6 is just the dilation. Remember the dilation. Remember the vertical stretch? Yeah, good point. Vertical stretch.
Explain where it comes from.
Because -6 is.
Just stretches it more vertically. Yeah. Yeah, just stretches it more vertically. Yeah. So the thing that's not moved is just stretched more further down.
Is -6, 0.
What would make it -6, 0? Then it would be x plus 6. And then, because remember, it's whatever the constant term is at the end dictates the y movement.
Yes.
So adding 4 would make it go up 4.
So that's why it's 0, because it's no field there.
In here it tells you the horizontal movement. And remember, it's counterintuitive. It's a reverse. This is good practice of the modelling stuff from last year, so it is a good question. Because if it's plus 6, it means it shifted back 6. But if you had something like x plus 2 minus, and the square there, minus 4, what would be the coordinate of that vertex for that?
Okay, Sarah. Oh, -2, -4. Oh, yes.
Because the horizontal movements, what's in the bracket?
0.
And it's always counterintuitive. The y movements and just the constant term at the end.
I'm listening to this.
You don't need to write that down. This was just good review. I'm writing down.
Get a pencil.
So that was just to reiterate why the coordinates of the vertex are 0, 0.
Am I driving the graph?
Yeah, draw that.
So we say there's a point of inflection. No, that's an absolute lie. There's a maximum at 0, 0.
Yep, there's a maximum at 0, 0, good. And then notice what it wanted overall. Use the first derivative to state over which intervals each function is increasing or decreasing. So here's an increasing interval here. So it's increasing over which.
The left side of the graph.
Yeah.
Infinity.
Good.
One of the crocodile thingies, x. The crocodile thingy to 0.
Good. Yeah.
Which way is the crocodile thingy facing?
So it's
Towards
increasing.
the x and then away from the x.
Yeah, the little arrows are always facing to the left.
Yeah.
Generally.
I knew that, but Sarah has to be specific.
Ah, you're
I
questioning
can't
it.
explain. It's called a less than sign and a crocodile.
The crocodile. Inequality signs are an even more messy way. Where is it decreasing? Over what interval is it decreasing?
0, crocodile sign. What?
Crocodile salad.
Sign, infinity sign.
But how can it be less than infinity when you know what infinity is?
Because
It's greater than infinity.
greater than any number.
It's greater than negative infinity.
Well,
No,
try to feel
but
jump on your throat bridge.
Sorry?
It just jumped on your throat.
Oh, how is it less than infinity? But from here to infinity. So from 0 to infinity. The x values are
But
less.
should it be like including that's fine, whatever.
No, it's good things to ask about. Good question. So this part here is actually our answers. This part here is actually our final answer in there.
What is the question?
Oh yeah, it said over what intervals is it increasing or decreasing? So
Do I do all of this?
yeah. This is quite intense, this kind of topic. Can you see why I kind of avoided it a bit?
I kind of love
Now
it.
there's no escaping it.
You think?
I love calculus.
I love it.
Okay, we'll finish up there and we'll continue next lesson. This topic's meant to take about 2 lessons, I'd say. It's pretty intense.
It's problem. I hate it.
Oh my.